Okay, folks, I'm going to work through a number of the problems from our in-class work to section 4.9, and we'll give this a shot. Please keep in mind that if you're watching this video, I don't think it's enough just to watch me do this, and I encourage you to struggle with these problems and struggle with them for a long time before watching me work out the solutions. That's the best way to learn. However, because we cannot meet in class at this time, I thought I'd go ahead and work through a number of these handouts with you. So please let me know if you have any questions. Alrighty, so I'd like to go ahead and just jump into these first couple of problems where we review how to find critical numbers. So remember what a critical number is. A critical number is a place where the first derivative is either 0 or where it's undefined, provided it's a point interior to the domain of the original function. So always before you do one of these problems, you should state what the domain of the original function is. In this case, this function is defined, well, the 2/3 operation, that's defined for all real numbers, but the square root operation only applies when the radicand is positive. So for that to work, we need x plus 7 to be greater than or equal to 0, which means we need x to be greater than or equal to -7. So the domain of this function goes from -7 to infinity. So there's the domain of this function. Now we want to go ahead and find the critical numbers. So to do that, we're going to first take the first derivative of this function to find the critical numbers of f. So let's do that. We're going to have a product rule here. Here's the first factor, here's the second factor. So I'm going to write this as the first, x to the 2/3, times the derivative of the second, which would be 1 over 2 times the square root of x plus 7. And then you don't have to write this, but technically there's a chain rule there, right? Because the argument inside the square root is more complicated than just an x. So this was my first, and then this is the derivative of the second. And I'm going to add to that the second, which is the square root of x plus 7, times the derivative of the first, which would be 2/3 x to the minus 1/3. So again, there was the second derivative of the first. So folks, all I did there was the product rule. And as far as the calculus is concerned, we're basically done with this problem. We just have to answer what the critical numbers are. But now we've got an algebra task ahead of us. And in this algebra task, we want to go ahead and rewrite this expression as a single fraction so we can easily identify where the derivative is either 0 or undefined. Let me clean this up just a little bit, and let's go ahead and do that. So cleaning up the first fraction, we get x to the 2/3 all over 2 square root of x plus 7. And cleaning up the second fraction, I end up with 2 square root of x plus 7 all over 3x to the 1/3. When I go ahead and bring this exponential term into the denominator, it ends up with a positive sign here. So what we'd now like to do is combine this together. We need a common denominator. So for the first factor, we're going to take x to the 2/3 all over 2 to the x plus 7, and it's missing the factor of 3x to the 1/3 all over 3x to the 1/3, so I'm going to multiply that to both the numerator and the denominator. And for the second term, we've got the 2 times the square root of x plus 7 all over 3x to the 1/3, and this is missing the factor of 2 radical x plus 7, so I'm going to multiply this by 2 square root of x plus 7 all over 2 square root of x plus 7. When I do that, what do I end up with? Oop, I meant for that to be blue, but I guess it's okay. What do I end up with? I end up with 3x plus 4 times x plus 7 all over my common denominator of 6 square root of x plus 7 times x to the 1/3. Okay. Or cleaning this up just one step more, we end up with 7x plus 7 all over x to the 1/3 times, let me write the 6 in front of that, 6x to the 1/3 times the square root of x plus 7. Okay. So folks, if you had any trouble with this algebra, let me know. But remember, all we're doing here is we're saying, hey, our derivative came out to be two fractions, like 1/3 plus 2/5. And we're combining those two fractions as a single expression by getting the appropriate common denominator. In this case, our common denominator was 6x to the 1/3 times the square root of x plus 7. So if I lost you on that, please let me know, and I'll be happy to go through that in more detail. So now we're ready to easily identify the critical numbers. The critical numbers are where f prime of x is equal to 0. Where does that happen? Where does f prime of x equal to 0? That happens when x is equal to -1, or where f prime of x is undefined. Well, f prime of x is undefined for all values to the left of -7 and including -7, or if it is 0. So is undefined for these values from -infinity to -7 and 0. Those are the places where, careful, not where it's defined, where it's undefined. Or put another way, what's the domain of f prime? The domain of f prime is from 7 to 0 unioned with 0 to infinity. Okay. So now at long last, I'm ready to state what the critical numbers are. What are the critical numbers of this function f? The critical numbers are x equals -1 and x is equal to 0. Okay. So let's be a little bit careful here, and let's look at who's included in the critical numbers and who's not. Okay. So we excluded x equals -1. How come? Because if I plug -1 into this derivative, I'm going to get out a 0. Also, though, notice what I'm also checking. Where is -1 in reference to the original domain of the function? -1 was an interior point in the original domain of the function. It wasn't a boundary point, and so that's why we get to include it as a critical number. Who else is included? Well, we're going to include 0. Why are we going to include 0? Because 0 is a place where the derivative is undefined. It's undefined at 0. And what was 0 in reference to the original function? Well, 0 was something in the interior of the domain of the original function. So we get to include it as a critical point. What do we not get to include as a critical point? We do not get to include 7. And you might have guessed 7 was a critical number, and I would say that it's, that should be -7, not 7. You might have thought that -7 was a critical number, and that's not a bad guess, but I'm telling you that technically it's not. How come? Because -7 was a boundary point of the domain of the original function, and even though the derivative is not defined now at that boundary point, since -7 wasn't an interior point to begin with, then we're not going to call it a critical number. And so the only critical numbers of the function f are at x equals -1, because that's what makes the derivative 0, or at x equals 0, because that's where the derivative is undefined. Okay, folks, so let's look at the next question. Very similar question. Here we're asked to find all critical numbers on the interval from -1 to 1. So really the only difference between these two problems is that here we've got a restricted interval. We've got our own domain that we're given as opposed to inferring the general domain of the function. So even though this function here is defined from -infinity to infinity, we're only going to be considering numbers on the interval from -1 to 1 as critical numbers. So let's go ahead and give this one a shot. So we've already got the domain of f. The domain of f, we're told, goes from -1 to 1. And then we're going to find the first derivative because we want to find the critical numbers. So we take the first derivative, and here again I've got a product rule. So here's the first times the derivative of the second plus the second times the derivative of the first. As far as the calculus goes, we're done with the calculus, but now we have to do some work to combine these two terms into a single fraction, and this is this challenging algebra that we've been practicing. So let me go ahead and rewrite this as 2x to the 2/3 plus, and then I'll have 4x minus 12 all over 3x to the positive 1/3, where I went ahead and distributed this factor of 2. I distributed that over to this parentheses, and I went ahead and brought this negative 1/3 down below the line and changed the sign to a positive 1/3. Okay, so now we want to go ahead, we're in the process of combining this as a single fraction. Well, we notice that the common denominator here will be x to the positive 3x to the positive 1/3. So I'm going to multiply that to make sure both terms have all factors of that common denominator. So in this case, I'm going to multiply this first term by 3x to the 1/3 all over 3x to the 1/3. And that will leave me with, for that first factor, that will leave me with 6x to the 1/3 all over 6x, just 6x, all over 3x to the 1/3. The second term was already good to go, so we just had 4x minus 12 all over 3x to the 1/3. So we're going to add together those two terms now that we've got a common denominator. And what do we end up with? Well, we end up with 10x minus 12 all over 3x to the 1/3. So we now ask the question, where is the first derivative, either 0 or undefined? Well, for f prime of x to equal 0, that would require 10x minus 12, the numerator of this fraction, to equal 0, which would happen when x is equal to 12/10 or when x is equal to 6/5. And where is the first derivative undefined? Well, it's undefined at x equals 0. Now, let's be careful. Now I'm ready to give the critical numbers of f on the interval from -1 to 1. So what are the critical numbers? What's the answer to this problem? The answer is just x equals 0 for the critical numbers of f on this interval. Let me ask you the question. Why didn't I include 6/5? After all, if I plug 6/5 into the first derivative, we've shown that it's going to output a 0. We've got a horizontal tangent line at x equals 6/5. Why don't I include that as a critical number? And the answer is because 6/5 is outside of the domain that I was given. Okay. So I want you to now go ahead and review your notes to number 52 from the section 4.1 class. Folks, if you don't review that, if you don't have those steps down, you will not necessarily be successful on these finding global maximum and global minimum problems. Okay. So please make sure you do that. Okay, so let's look at number 4 now, where we're asked to find the global extrema for this function. This is the same function we were just looking at on the interval from -1 to 1. So here we go. The first thing is, does the extreme value theorem apply in this instance? The way I've mentioned this in class is that I've said we're about to go looking for a needle in a haystack. That is, we're about to go looking for global extrema, and it's nice to know that those global extrema exist before we go looking for them. Otherwise, we may be searching for something that doesn't exist. So how do I know that f must attain both its local max and local min? Excuse me, that's an incorrect statement. How do I know that x must attain both its global maximum and global minimum on this interval? Well, there's two things to check. Notice that f is continuous on its definition, on its domain. It's a continuous function, and -1 to 1 is a closed interval. So yes, by the extreme value theorem, f must attain both its global maximum and its global minimum somewhere on this interval. Now, where could that global maximum or global minimum be? Well, it could be at one of the two endpoints, and we've seen that instance, and we'll test that situation separately. Or where else could it happen? It could happen where maybe, let's in context of a global maximum, it might happen at a place like this. But what do we know happens to a function if it's differentiable there? Its derivative is 0. What if it's not differentiable there? What if we had, say, a cusp? That could potentially be the global maximum. But what would be the derivative there? Well, the derivative we would find is undefined there. And so that's why we're testing those critical numbers when we go hunting for global maximums and global minimums. So 2, give the critical numbers of the function f. And this is the same question that we had up above in number 2. And so we found that there was just this one critical number of x equals 0. Okay. Now step 3, folks, is to evaluate the critical numbers in the function. So let's evaluate f of 0. and evaluate the endpoints. So we're going to evaluate f of 1 and f of negative 1. Now careful, why are we evaluating f of 0? Because it's a critical number of f. That's why we're plugging 0 into the function to see what its corresponding y value is. Why are we plugging in 1 and negative 1 into this function? Because we're checking to see what the value is at the endpoint. So this is checking the endpoints. Careful, folks, when you do all this work for critical numbers, it's sometimes easy to forget that you also have to check your endpoints. Okay, so let's go ahead and plug 0 into this function. Well, if we plug in 0, it's going to output as 0. Let's plug in 1. If we plug in 1 into this function, it's going to output, let's see here, 1 to the 2/3 times 2 times 1 minus 3. What's that? Well, that's 1 to the 2/3 power is just 1. And that gives us negative 1 for that value. And if we plug in negative 1, we'd get negative 1 to the 2/3 power times 2 times negative 1 minus 3, which gives us negative 1 squared is positive 1. Take the cube root of that as 1. And so we end up with negative 5. Okay. So what are our global extrema? We've just shown, and I'm running out of room here, that x equals 0 is a global max. To f on the interval from -1 to 1. That is, if I plug 0 into this function, I'm going to get out a y value, in this case of 0, but that is the largest y value I will get out. There are no values in between negative 1 and 1, such as maybe negative 0.2 or positive 2/5 or something like that. There is no other number in this interval that will output a number larger than it outputs when I plug in 0. That's what it means for x equals 0 to be a global maximum. So what else? Well, we also see that x equals negative 1 is a global minimum. Why is that? Of these three candidates for global max and global min, of these three candidates, negative 1 is the one that spat out the largest negative number, or the most negative number there, or the smallest number, if you will, on the number line, the one that's furthest to the left. So x equals negative 1 is our global minimum. Careful, not global minimum for wherever this function exists, but on the interval that we were considering from negative 1 to 1. And that's really how you should represent your solution to this problem. Okay. So folks, make sure you do number 5, where you explore the Desmos demonstration to confirm your answers to these questions, and we'll pick up later. So folks, let's go ahead and pick up with number 6 here. And this is a question we've seen before, where I give you a function and I ask you where does it attain its absolute maximum and absolute minimum. So the first thing you should ask yourself is, does the extreme value theorem apply? That is, if you're going to go looking for that needle in a haystack, you want to make sure that it exists. If you're going to go looking for absolute maximums and absolute minimums, you want to make sure that they exist. So what do we say? Well, we say f is continuous on -3 to 2, so the extreme value theorem applies. That is, x is a continuous function on its domain, and that domain is a closed bounded interval. So now we go looking for our global max and global min, and to do that, there's really two things we check. We find the critical numbers and test them, and what else do we test? We test the endpoints as well. So let's go look for your critical numbers. So to find the critical numbers of the function f, what am I going to do? I'm going to take its derivative, and in this case f prime of x is equal to 5x to the 4th plus 28 x cubed plus 36x squared, and I'm going to look for where this derivative is either 0 or where it's undefined. Well, notice that this function, in this case, is a polynomial function, and it's everywhere defined. So f prime of x is defined on its interior, or we'll just go say, well, yeah, we'll say on the interior from -3 to 2. Okay? So it's everywhere defined, but Where is it 0? F prime of x equals 0. That would happen if 0 is equal to 5x to the fourth plus 28x cubed plus 36x squared. What can I do now? I can factor out an x squared. That'll leave me with 5x squared plus 28x plus 36. And then this factors. Folks, if you're rusty with factoring, please see me in a Zoom office hours and we can maybe do some factoring drills. But what I recommend doing is doing some practicing with factoring so that you're comfortable with factoring just a trinomial like this one. This factors to be 5x and x. And let's see here, this is going to be 2, and this will be 18. The signs are all positive because this tells me the signs are the same. This tells me that then both must be positive. That's positive 36. Okay. So now we've given f in f's derivative, f prime, in factored form, and so we see that the critical numbers of f prime on the interval from -3 to 2 are what? They are x equals 0, because if I plug in a 0, that factor makes the entire derivative 0, or they are x equals -2. If I plug in -2, that'll make the whole thing 0. It will also be 0 if I plug in x equals -18/5 into this function. But why am I not concerned about that? Because -18/5 is approximately -3 points, or actually not approximately, it is -3.6, and -3.6 lies outside of our interval that we're currently considering. Okay. So those are the two critical numbers. Now I'm ready to do the answering of the question. We're going to plug in 0 into the original function, and we're going to plug in -2 into the original function. Now why am I plugging in both those numbers? I'm plugging in both those numbers because they were critical numbers of f on the interval from -3 to 2. What else am I going to plug into this function? I'm going to plug in -3, and I'm going to plug in 2 into this function. And why am I plugging in those two values? Because those were the endpoints of the interval. You've got to check both the critical numbers and the endpoints because those are the potential locations for the global maximum and global minimum. Okay. So let's see here. If I plug in 0 into this function, it's going to spit out a 0. If I plug in -2, it'll spit out, let's see here, -2 and let's see, 2 and -2 is, that's -8. So that's -16. So that spits out a -16. And if I plug in -3, it spits out 0. And if I plug in 2, let's see here, we've got 6 and 5 is 30. And we get 8 times 30, which is 240. So folks, double check my arithmetic on that, but I think we're okay. So where does f have a critical max, or where does f have a global max? F has a global max at x equals 2. Why? Because that gave me the largest y value for this function. And f has a global min at x equals -2. Why? Because that gave me the smallest y value on that interval, and that is my solution to this problem. Folks, I want to say one thing real quick. When I write these problems, I try to make them something that's easy for you to work with. And so for that reason, there's not a whole lot of potential numbers that you would plug into this function. So for example, if you were plugging in only nice numbers into this function, you might plug in -3, -2, -1, 0, 1, and 2. You might just plug in those nice numbers into this function, and then you could check your answers. Now, could you from that list maybe guess what the global max and global min is? Yes, that's correct, but you've not done the correct procedure here. So it's absolutely essential that you follow this procedure that we're doing. Otherwise, I would just give you a more difficult problem to do, in which case that method of just plugging in nice numbers certainly wouldn't work. So folks, that concludes the warm-up. I'm going to go ahead and continue some other questions here through this video. Okay, folks, now let's look at number 24 in the middle of the growing your calculus skills. We're asked to find, careful here, this notation is important, not an antiderivative of f of x. We're asked to find the antiderivative of f of x. And so what is the antiderivative? It's capital F of x is equal to what function, when we take its derivative, will give us 3x squared? What function, when we take its derivative, will give us 3x squared? Well, the answer is x cubed is one of them, but so would be, say, x cubed plus 2, or x cubed minus 5, or x cubed plus the square root of 6. There are many functions that when I take their derivative will give me 3x squared. And what are we looking for in this problem? We're looking for the family of functions that give that as an antiderivative. So x cubed plus c is that general antiderivative. That's what we call the antiderivative. So notice I needed to have this plus c in this solution. It needs to be a family of functions and not just one function. So if you miss that plus c, you'll be docked on this problem. Okay, now we're asked to graph f of x for a few different parameters. So let's go ahead and graph f of x is equal to x cubed plus 0, which would just be x cubed. And we'll graph this function, let's call it g of x, is equal to x cubed plus 1. We'll graph that function. And h of x is equal to x cubed minus 2. So let's graph all three of these functions on the same graph system, the same coordinate system. So let's see here. Here's x, and here's y. And so for a c value of 0, we just are graphing the function x cubed. Well, that's the cubic function that looks something like that. That's what we get when c is equal to 0. And when c is equal to 1, for this second one, let me do that in a different color. For c is equal to 1, we're going to graph the function x cubed plus 1. So it has a y-intercept of 1, but other than that, the shape of this curve is identical to the other one. And what's important to notice here is, could this green curve ever intersect this blue curve? Well, no, because they're the exact same shape. One is just shifted up 1 unit from the origin, while the other one is at the origin. So those two functions are identical, with the exception of one being a translation of the other, or one is shifted up from the other. Other than that, their shapes are identical. Let's go ahead and graph the third one when c is equal to negative 2. That's this function right here, x cubed minus 2. And let's see here, to plot that, we could go ahead and drop down 2 from the original point of 0, 0, and we can go ahead and sketch the graph. This is when c is equal to minus 2. And I think I forgot to label this. This first one was when c is equal to 1. These are sometimes called level curves of this function. Notice that I've selected different constants for my arbitrary constant c, but in all cases this function has the exact same shape. Why is that? Well, because for it to have the exact same shape, it has to have the same rate of change. Any one of these has to have the same rate of change, and they all do. They all have the same derivative of 3x squared. So the second question, or actually part C here, asks us what are some properties we notice about these curves of f of x. Okay, so this is something that I just said in the previous example. One, notice that they all have the same shape. Okay? And that one way to say that, or one way to realize that they all have the same shape, is that they all have the same rate of change. What do I mean by the rate of change? I mean they all have the same derivative. The derivative of all of these, f prime of x, is our given f of x, which is just 3x squared. They all have the same derivative. Okay? So notice that because they all have the same shape, but they all have different y-intercepts, then these curves will never intersect. And that's probably the biggest takeaway point from this example. These curves will never intersect. So this next problem asks us to find capital F of x so that f of 1 is equal to 9. Well, if f of 1 is equal to 9, that's the same thing as saying that this curve must pass through the ordered pair 1, 9. So let's look at these. We drew these curves here. Does any one of them pass through the ordered pair 1, 9? Well, let's see here. I don't think so. If I were to plug 1 into this first one, x cubed, if I plug in 1, it just spits out a 1. If I plug in a 1 into this second one, it would spit out 1 cubed plus 1, or it would spit out 2. And if I plug in 1 into this third one, it would spit out 1 cubed minus 2, or negative 1. So that is, this goes through the ordered pair 1 minus 1, this goes through the ordered pair 1, 1, and this goes through the ordered pair, it's kind of hard to see here, the graph's getting a little cluttered, but that group goes through the ordered pair 1, 2. Okay? So none of those are the curves, even though they've got the same shape. So what did we say about our function? We said our function, capital F of x, is x cubed plus c. So what do we not know? We don't know what that arbitrary constant is, c. So we need to solve for that c. And the way we do that is we replace the functional value with 9, and we replace the x value with the domain input of 1. And so we get that 9 must equal 1 cubed minus c. Plus c. I dropped that plus sign. Plus c. And so we end up with c must equal 8. So what is our answer? Our answer for this particular solution curve is x cubed plus 8. That's what we mean when we say we want to find the particular solution from this family of solutions so that we satisfy this given condition. Okay? So in general, when you go to find the antiderivative of a function, you're going to have an entire family of functions, some of which I've drawn in this graph here. Okay? But sometimes we want to specify which member of that family of functions do we want, and for us to be able to figure that out, we have to be given one particular point of interest. Okay? So we call this an initial condition, or some other condition for this function, and from that we're able to solve for that constant. Now it's not a family of curves, so it's certainly a family of curves all of which have the derivative of 3x squared, but it's only one of those curves that has the derivative 3x squared and passes through the ordered pair 1, 9. Because if these curves never intersect, which is what we said, that was the big conclusion from C, then only one of them can pass through the ordered pair 1, 9, and this is the one that does that. Okay? So folks, I went ahead and worked number 25. The first thing I did was I just rewrote the derivative expression to make it a little bit easier to read. Sometimes people have a hard time reading that expression. 3x over 2, that's just 3 halves x, right, or minus 3 halves x in this case. So I just rewrote the derivative, and then from here to here, from this line to this line, I took the antiderivative of this function. So I asked myself, which functions when I take the derivative give me e to the x? The answer is e to the x. What function when I take its derivative gives me the secant of x tangent of x? And the answer is the secant of x. And then I said, what function when I take its derivative gives me minus 3 halves x? And the answer is minus 3/4 x to the second. Now you might have a little bit of trouble with that one, but remember you can use your power rule for antidifferentiation, which says that if f of x is equal to x to the n, its antiderivative is equal to 1 over n plus 1, x to the n plus 1, and this holds for n not equal to negative 1. So that's the power rule that I used to calculate this antiderivative. If you have questions on that, please see me. Okay? Now, at this point, what have I done? I've given the antiderivative as a family of functions. Okay? Any function for any choice of constant c here, when I take its derivative, will give me the blue function f prime of x. But I don't want just any of them. I want the specific one amongst them that satisfies this condition here, that when you plug in a 0, it spits out an 8. So to figure out which one I went ahead and plugged in a 0. Sorry folks, I got interrupted. I'm not exactly sure where I left off. So we ended up with this as our this is our function as an antiderivative. This is the family of functions, and then we want to select the specific function we want. So we want the one where when we plug in a 0, it outputs an 8. So we set this family of functions equal to 8, replacing the x's in that expression with 0, and then we solve for the corresponding c value that will make that true. Now that we've done all that, we can go ahead and give the answer. This is the answer to the problem. Careful, the answer to the problem isn't just what c is. The answer to the problem is the specific function. F of x equals e to the x plus the secant of x minus 3/4 x squared plus 6. That's what we found the answer to be in this problem. Okay. So now let's go ahead and answer number 26 together. Let's take a look at this. So in this case, folks, for number 26, it's a little bit different than we've seen before. We're given this, what the second derivative of the function should come out to be, and we're asked to find the original function. So although it's a new question, it's really just the same procedure we've been doing. We're just going to have to find two successive antiderivatives of f double prime. If we find one antiderivative of f double prime, that will lead us to a family of functions for f prime. And if we find the antiderivative of that, it will lead us to another family of functions for f. So we're going to have to antidifferentiate twice here. So we would find out that f prime of x is equal to 4x to the third plus 3x squared minus 4x plus c. Normally I just write plus c. In this case I'm going to write plus c1 here because you're going to see I might have multiple constants in this problem. Okay. So folks, if I did that a little bit fast because we're just getting used to this, I'm doing the antiderivative power rule. So I'm doing the power rule for antidifferentiation here that says, for instance, to evaluate the antiderivative of this power function, I'm going to add 1 to the exponent, making it 3, and then divide by the new exponent. So I took 12 divided by 3, and that's what gave me 4. Okay. So that got us to the family of functions that represents f prime of x. Now let's go ahead and give the family of functions that represents just f of x by taking the antiderivative of our most recent answer. So if I take the antiderivative of f prime, I'm left with x to the fourth plus x cubed minus 2x squared plus, careful, how do I do this? Well, when I take the antiderivative of c1, or any constant, what am I left with? The antiderivative of a constant function is a linear function. And double check this. Take the derivative of c1 times x. What do you get? You just get c1. So yep, we're on the right track. Now, again, I'm looking for a family of functions, so I need a plus c2 there, because this c2 comes from when I took the antiderivative a second time. Okay. So now we've given the antiderivative. This is the antiderivative of f prime, but we specifically want this function to satisfy these two conditions here. That is, when I plug in a 0, I want it to output a 4. Well, that would mean that 4 would be equal to 0 to the fourth plus 0 to the third minus 2 times 0 squared plus c1 times 0 plus c2. So that would mean that c2 is equal to 4. So we know what c2 is. Now let's go ahead and see, let's see here. Well, we could restate f of x now as x to the fourth plus x cubed minus 2x squared plus c1x plus, instead of c2, I've learned that that needs to be 4. Okay. But now we need to figure out what c1 of x is. Well, luckily we've been given another initial condition, and so we can go ahead and find out what c1 needs to be. I know that if I plug in a 1, it needs to output a 1, so that tells me that this statement needs to hold. That 1 on the left-hand side needs to equal 1 to the fourth plus 1 to the third minus 2 times 1 squared plus c1 times 1 plus 4, or if you clean this whole thing up, we end up with 1 is equal to, let's see here, that's 1 plus 1 minus 2, which is 0, plus 4, so 4 plus c1, or that c1 is equal to negative 3. So finally we can give our answer as the function f of x is equal to x to the fourth plus x cubed minus 2x squared minus 3x plus 4, and there is our solution This is the function that when I take its derivative twice will give me 12x squared plus 6x minus 4. And if I plug in a 0 to it, it spits out a 4. And if I plug in a 1 into it, it spits out 1. Folks, let me know if you have any questions over this, and we'll continue on in a moment. So folks, in number 27 here, we have the exact same function, but the way we were given the initial conditions is slightly different. And so I've gone ahead and worked that through for you, and I'll let you take a look at it. The only difference between the two is really that when I go ahead and find out what f prime of x is by taking a first antiderivative, I'm able to solve for that unknown constant c1 in the first derivative because I was given a statement about the first derivative there. So I go ahead and plug in the order pair 0 for x and 7 for f prime of x, and I'm able to solve for that first constant. And so before I even go trying to find the original function, I'm back to a function without any constants in it. Then I went ahead and took the antiderivative of that answer and got an expression with a c2 in it. Then I can use this second initial condition to help me solve for c2. And this is what we end up with as a final answer. So pause the video, take some time, and see if that makes sense. Okay, folks, so let's look at this next question, and this is a physics question where we're given an acceleration of a particle. So if you remember back when we first did these motion questions, I gave you the position function and then would sometimes ask you to come up with either the velocity function or the acceleration function. In this case, we're working the problem differently, where I'm giving you the acceleration function and you're asked to come up with the position or the displacement function. So let's see what we can do here. We're told that a of t in this problem, that a of t, let me grab a different pen, that a of t is equal to 6t plus 4. Well, we know that the derivative of the velocity is the acceleration, so the antiderivative of the acceleration function then is the velocity function. So we end up with v of t then would be what? Well, if I take the antiderivative of 6t, I end up with 3t squared plus 4t plus some unknown constant, c. But I was told that the initial velocity is negative 6 centimeters per second. That is, when t is 0, this is traveling at negative 6 centimeters per second. So we end up with negative 6 equals 3 times 0 squared plus 4 times 0 plus c. And so we find that c would have to equal negative 6. By the way, you might be starting to see a pattern for initial conditions. If it's a polynomial and the condition has to do with when time is 0 or when x is 0, then it's very easy to solve for that c value. So we now know that our velocity function in its entirety is v of t equals 3t squared plus 4t minus 6. That's our velocity function. But we're asked to find the displacement function, so what do we need to do? We need to go ahead and take the antiderivative of the velocity function. Remember, if the derivative of the displacement function is the velocity function, then flipping that around, the antiderivative of the velocity function is the displacement function. And so we get that s of t would be equal to t cubed plus 2t squared minus 6t plus some other constant. And here we were told that our initial displacement was 6 centimeters to the right, so we know that s of 0, excuse me, I said 6, I meant 9, s of 0 is equal to 9, and so we end up with 9 is equal to 0 cubed plus 2 times 0 squared minus 6 times 0 plus c1, or that c1 is equal to 9. So at long last we're able to give our solution to this problem. What's our solution? Our solution is that s of t is equal to t cubed plus 2t squared minus 6t plus 9. That is the specific position function that when you find its acceleration, you would find that's its acceleration, and initially it's got a displacement of 9 centimeters to the right, and initially it's got a velocity of negative 6 centimeters per second. So this is the one function that does that. So folks, let's look at number 32, the last question on here, and it's here that we introduce some new notation. Really, it's just new notation. There's no new concept here. It's just rather than writing capital F of x as the antiderivative of an expression, we're going to write the antiderivative of little f of x. So, for example, we would write that the antiderivative of the cosine of x dx is equal to what? Well, the answer is the sine of x plus c. Why? Because any one of these functions in this family of functions, when I take its derivative, will give me back to the integrand, the expression inside the integral there, which is what we wanted to come up with. Okay. So make sure you practice this vocabulary. That's what I have you go through here. I think all the answers are there in the line above it. But let's go ahead and evaluate the following indefinite integrals. So if we evaluate this one, we can evaluate the antiderivative term-wise. And so we would end up with x to the 6th plus 7/2 x squared plus the natural log of the absolute value of x plus c. Be very careful. Remember, I don't use the power rule on the function 1 over x. The power rule doesn't apply to the function 1 over x. Instead, I just say, well, what function when I took its derivative gave me 1 over x? And for the positive numbers, that was the natural log of x. But to give the entire function over the entire domain of 1 over x, we would use the natural log of the absolute value of x. That's the antiderivative of this function. This problem here says to give the antiderivative of secant squared plus 7e to the x. Well, that's going to be the tangent of x plus 7e to the x plus c. Why? Because the derivative of the tangent is secant squared. The derivative of 7e to the x is 7e to the x. And the derivative of constant zeroes out. Okay. So folks, it's exceptionally important that you work through number 3 here. I give you all the information you need. So I'm going to let you go ahead and do that. So folks, here we have the answer to number 3. Do make sure you work through that. That's a very common test question for me to ask. So make sure you understand all of those steps. For number 4, the antiderivative of this function would be the arctangent of x plus c. Why? Because what's the derivative of the arctangent of x? The derivative of the arctangent of x is 1 over 1 plus x squared. So that means that the antiderivative of 1 over 1 plus x squared dx is the arctan of x plus c. Okay. So let's look at number 5. What are we going to do there? Well, we're just going to do some clever rearranging of things. Notice I can rewrite this integral as the integral of 4 cosine x all over the sine of x times all over the sine squared of x plus the sine squared of x all over the sine squared of x. So I just broke this up into 2 fractions, dx. And this first expression here I could rewrite as 4 times 1 over the sine of x times the cosine of x all over the sine of x. And the second expression I could rewrite as 1. So folks, do double check, make sure that this makes sense to you. If you don't believe me, go ahead and multiply out your numerators. You'll have 4 cosine x. Multiply out your denominators, you'd have sine squared of x. So that's how we could rewrite this problem. Why am I doing it that way? Because I'm trying to put it in terms of my elementary antiderivative rules. So I can now go ahead and rewrite this as the integral of 4. What's another way of writing the sine? Well, 1 over the sine of x. We could write that as the cosecant of x. And what's another way of writing the cosine of x over the sine of x? We can write that as the cotangent of x plus 1 dx. And now, and only now, am I ready to evaluate this antiderivative. Okay? By the way, I should now put parentheses inside my integrand. That's a good habit to get into, so that the integrand should be in parentheses there, and in parentheses there. You don't have to do that, but it's a good habit to get into that. Okay, so what function, when I take its derivative, gives me 4 cosecant x cotangent x? Well, that is 4 times the minus 4 times the cosecant of x. Remember, the derivative of the cosecant of x is equal to minus cosecant x times the cotangent x. And so if I ask you what's the antiderivative of 4 cosecant x cotangent x, the answer is minus 4 cosecant x. Plus, what's the antiderivative of 1? What's the antiderivative of 1? It is just x and then plus c. Do not forget your plus c on that answer. So folks, there's a quick, well, I don't know how quick it was, an hour-long video over our in-class work. Please take a look at that and let me know if you have any questions.